Welcome to Oracle APM tutorial series. Application Performance Monitoring is a service in Oracle Cloud Infrastructure that provides a set of solutions including distributed tracing, real user monitoring, and synthetic monitoring. This recording covers distributed tracing, which is a part 2 of the tutorial. My name is Yutaka Takatsu. I'm one of the product managers in Observability and Management Product Management team in Oracle Cloud Infrastructure. The tutorial consists of 5 different video recordings which you can find in this Oracle channel. Each recording is about 20 to 30 minutes long. Please find the video links to the other chapters from the description in this video. This is a recording of Part 2, Distributed Tracing. The Chapter 4 is Distributed Tracing Fundamentals. This is an optional chapter to review the basic and general information of microservices and distributed tracing. So if you are already familiar with these topics, please skip this chapter and go to the next chapter 5 to see how distributed tracing works in APM. To understand distributed tracing fundamentals, let's start by discussing why do we need distributed tracing. To do so, let me go 15 years back to review the history of the software development architecture. Traditionally, applications are built in a single monolithic architecture, which typically have 3-tier layers: presentation, application, and data layers. The applications are often written in a single programming language and run on a single platform, having a large block of code that is compiled into a single program, such as jar or WAR files, for example. And because of the single code base, compared to other more complex architecture, it is easier to understand what is happening in the application at runtime. However, the trend has changed with the emergence of the cloud computing technologies, as the application had to grow larger and more complex to respond to the expectation from the customers. As a result, the large monolithic code base became inefficient to maintain. It also prevented the development teams from working independently, which resulted in difficulties making changes in the application. Because whenever the change was made, the entire application must be rebuilt. All these resulted in productivity issues and slowed down the development. That was where microservices architecture came into play. Microservices decomposed the large monolith into independently deployable smaller services. Each service was built independently and worked together to accomplish the business logic. The services may be written in a different programming language, can be running on different platforms and technologies, and communicate with each other through API endpoints with HTTP. Microservices architecture provides portability and scalability, as each service can be individually scaled or deployed without the need of concerning other requirements. It is fault-tolerable as the services are loosely coupled with each other. Therefore, a failure in one service only has a limited impact on other services. It is also technology agnostic because it does not rely on a specific programming language or technology. Compared to monolithic architecture, microservices architecture allows faster product delivery. So microservices are great, but the downside of it is because of the complexity of the architecture, it is hard to trace down the behaviors of the requests. Let's bring back the monolithic application back on the screen. In an application with a single process architecture, it is relatively easy to trace the request to find what went wrong in a thread. For example, using traditional tracing tools, you can start from tracing the user session, narrow down to the stack trace in the application's JVM, and trace all the way down to the database. However, this is not the case when it comes to microservices. In applications built on distributed microservices architecture, multiple services communicate with each other in complex ways. These services can be running simultaneously in different servers on different platforms, which makes it hard to trace the workflow and identify the root cause of the problems. It has increased number of point of failures and increased time to diagnose and fix problems. The questions like how long the request took to complete in each service, or how much time was spent to connect to other service, these questions need to be answered as well. This is where the distributed tracing plays an important role. Distributed tracing is a solution for tracing requests in a distributed software architecture. It tracks the workflow of a single request and collects data from the services as the request goes down the stream. It basically tells you a story of how the request flows through your distributed system and what experience did they have by going through it. Let's take a close look at the trace view. Every var in the flow is called span, and a group of span is called trace. Span is a fundamental unit of distributed trace and represents an operation taking place within a microservice or a function call. Trace is a complete flow of the request and includes one or more spans within that trace. When a user or an API call makes a request in a distributed application the first time, a span is created. This is a root span. This is a first span in the request, so a unique trace ID is assigned. In this example, that is 000. It also gets a unique span ID for the span itself. When the same request makes another call within the distributed system, it creates another span that represents an operation. This is a child span. Because they are related, the same trace ID is assigned to the new span. Also, the span ID of the parent span is passed on to the new span. This becomes a parent span ID. A unique span ID is assigned for this span as well. So this is how the spans are chained and become traceable. When the request creates another span, the trace ID and the parent span ID are passed on to this new span as well, and the unique span ID is assigned. So a single trace can have many spans which are placed in the order they were called. That is how the trace can have a complete end-to-end workflow of a request in a distributed system. And there can be multiple spans within a single microservice that create child spans in another microservice and communicate with REST API over HTTP. Still in this case, the events within a single request are correlated because the span context of the parent spans is bundled and transferred to a child span via HTTP header across service boundaries. Then what are the standards that distributed tracing has? There is open tracing, which is a vendor-neutral standard. Basically, it's a set of APIs provided for DevOps engineers to instrument distributed tracing. There is also Open Census, which is a set of libraries. And Open Telemetry is a new standard that is Open Tracing and Open Census combined. It has a single set of APIs and libraries for collecting distributed traces. And Oracle's APM solution supports Open Tracing and Open Telemetry. In the next chapter, we'll jump into the distributed tracing solution in Oracle APM. This is Chapter 5, Distributed Tracing. So we'll discuss how distributed tracing works in Oracle Cloud APM, how the data is collected from different data sources, and understand key functionalities. We discussed the fundamentals of distributed tracing in the previous chapter. Let's quickly recap the mechanism of how distributed tracing works within the picture of Oracle Cloud APM architecture. There are three boxes in the screen with a database icon at the right. This is your microservices application. You have a web user interface and two microservices with a database. At the lower side of the screen, there is Oracle Cloud and APM. APM is a service provided in Oracle Cloud infrastructure. In the application, a user initiates a request through a browser. A browser agent, which is instrumented at the front-end side of the application, creates a new trace, which can have one or more spans. The first span is called a root span. As mentioned in the previous chapter, spans can be correlated over service boundaries. Span context information such as trace ID, span ID, and other properties will be bundled in HTTP header and transferred over HTTP call. This way, the spans in the browser and the spans in the microservices know they are connected within a single trace. Likewise, spans in microservice A can call another microservice and create child spans in that service. Microservice B then makes a database call and creates SQL spans. As each call returns, the tracer sends individual spans to APM. Server spans are incoming calls such as incoming HTTP requests or remote procedure calls. And client spans refer to outgoing calls such as outgoing HTTP requests or database calls. Traces and spans are sent to the APM collector in Oracle Cloud. Each type of spans include a list of dimensions that can help you to filter or group the spans that you can use for analysis. So this is how distributed tracing works in APM at a high level. Once the data is collected, you can use rich user interface in the APM console to visualize the data. You can see traces and spans in Trace Explorer, then use SQL-like query language to narrow down the selection to perform deep dive analysis on your application's performance. Let's now go understand how the data is collected in more depth. APM collects data from predefined data sources for Java applications, or use open source tracers for non-Java applications from both server-side and front-end. APM also collects data directly using APIs. Say, for example, you have an application written in Python. APM supports any open telemetry tracers such as Jaeger or Zipkin. Here in this case, you can use Zipkin tracer, which is one of the open source tracers. To do so, first you need to write some code to instrument the application with the tracer, which generates spans and upload the tracing data to APM. And we have online tutorials that walk you through the instrumentation step by step. So for more details on how to instrument Python with Zipkin Tracer, please see our documentation in the link. Okay, so that was when you have a non-Java application. But you may also have a Java application with open tracing enabled, such as Helidon-based microservices. In that case, APM has its own tracer dedicated for Java. So you can use the APM Java tracer to have additional information out of the box. So for example, if the application is deployed on a Kubernetes cluster in Oracle Cloud, it tells you which compute node a pod is actually running. So here, first you need to apply a code instrumentation of the Java files that generates spans which the tracer can upload to APM. Another case is when a Java application is running with older J2EE application servers such as WebLogic. You cannot directly deploy the tracers to these systems because they don't have any built-in support for open tracing. In this case, you can use APM Java Agent instead of the tracer. Java Agent, in fact, uses the same APM Java tracer internally, and it does automatic bytecode instrumentation on top of that. What this means is that unlike the Java tracer, which needs to manually write code to Java files, the probes, which is an intermediate program that resides in the Java agent, automatically kicked in and create spans and send them to APM. Optionally, you can use aggregator to aggregate the incoming spans. This can be useful in case the application runs in a cluster and uses many servers. There is also a browser agent that is a set of lines of JavaScript code. You need to ingest the JavaScript into the index.html file of the application. APM also supports OpenAPI, which is a description format for REST APIs. For example, you can use it with function as a service. To do so, you can upload your code to Oracle Cloud and create a function. Function as a service in Oracle Cloud has integrated with APM. You can log on to Oracle Cloud Console and enable the tracing, and that will send a span to the APM service. Let's see a list of key functionalities of APM in distributed tracing. APM accepts all spans of all traces. Unlike many other distributed tracing tools which collect data with sampling, APM is built to send all data of all instances of every invocation of code so that you will not miss any critical errors or latency you might have in application when analyzing the data. APM still, however, allows you to enable the sampling as an option. APM supports open tracing, which is a vendor-neutral standard for instrumenting distributed applications. It also supports open telemetry, which is a newer standard to support hundreds of types of applications and languages. APM stores data in the Oracle database, which allows you to run both real-time and historical analysis. You can run queries comparing the data between the current workload and the baseline workload that was captured several weeks ago, for example. APM provides a SQL-like language that is specialized to run queries against distributed tracing data, like traces and spans. You can ask questions like, show me all the spans that are failing in North America, for example. Dimensions are attributes of the spans. There are more than 100 out-of-the-box dimensions that you can use to query and filter traces and spans in the Trace Explorer. Trace Explorer user interface includes a service topology view, which you can visualize the relation among the spans, as well as a traditional Gantt chart style dashboard that lists the spans as bars in a hierarchical view to show durations and the dependencies of them. Apdex score, or Application Performance Index, is a measurement that tells you how well the application is doing. In APM, you can use Apdex as a metric in a query or as a dimension to filter or analyze the data in Trace Explorer. APM collects a lot of metrics by default. In addition, you can create your own custom metrics out of the data collected. Once the custom metric is created, the metric data will be sent to the monitoring service. You can also detect anomalies on metrics and get an alert when the data went out of the range of the certain criteria. That was a quick introduction of the key functionalities of the distributed tracing in APM. We'll see more details on these topics in the later chapters in this tutorial. Moving on to Chapter 6, Trace Explorer, which is a core functionality in the APM service. In this chapter, we'll talk about Trace Explorer capabilities such as query language, various types of views, and integration with Oracle functions. Once you instrument your application with a tracer and upload the data to APM, you can visualize and diagnose the traces and spans in Trace Explorer in Oracle Cloud Console. Trace Explorer allows you to monitor traces and spans and view a large set of data which is collected by different data sources, and use data information for error or slowness detection, also for troubleshooting and analysis. The user interface of Trace Explorer is displayed on the screen. Once the page is loaded, you'll need to select the compartment and APM domain, as each domain has different data stored. Upper side of the page, there is a window where you can type down a query to extract the desired list of traces and spans. Here you can write your own query, but for your convenience, there are out-of-the-box queries predefined in the Quick Pick tabs. These are the queries commonly used by customers. The query result is displayed in the main portion of the page. You can see the list of traces with the context such as operation name, status, start name, duration, and the number of spans and error count. You can sort the list by clicking the column. So for example, you can say, show me the slowest traces to the top of the list. You can see metrics and dimensions in the field section. They can be used in the query to filter the selection of the data. You can also change the time range, such as the last 15 minutes or last 24 hours, or pick a specific range of time and load the data that was collected at the time to the screen. To retrieve a set of data and load onto the Trace Explorer screen, you will need to use a query. You can either use the predefined queries that you can access by selecting the Quick Pick tabs, or write your own query in the syntax shown in the screen. The queries in the Trace Explorer consist of the clauses and dimensions, which are the attributes defined by tagging the spans. You can find the list of available dimensions in the field section in the Trace Explorer main page. As for the best practice for customizing query, you can use one of the predefined queries as a template and edit. Please see an example in the screen. On top of one of the predefined queries, I added a condition in the where clause to retrieve the span only when the aptX level is frustrated. Then you can save the query so that you can reuse it the next time. Another interesting feature of Trace Explorer is Geo Map view. You can switch the visualization of the query result and see the trace data in a map view by clicking the globe icon on the screen to see from which countries the requests were made and what were the performance in each country. The Geo Map view is one of the predefined views which lets you pinpoint your application status and issues by global locations. In this example, duration is currently selected as the metric, so the darker the color, the slower the connection time in that region. And you can select different metrics, for example, span errors, to see users from which country are experiencing the most errors. You can also click each country to narrow down to the states and province. By hovering the mouse icon over the state of California in this example, the map shows the cluster details of the trace information in the selected region, such as total number of errors or average duration. Next, let's see a real-world use case how we can use Trace Explorer to analyze a performance issue. So I am back at the default view of Trace Explorer, having a list of traces. These are the traces that were collected in the last 15 minutes, and now I can see some of them are taking a lot of time. This particular trace at the top row took 44 seconds to execute. If this was your system, likely the next you want to do is to find out why the trace was slow. So let's narrow down to see the individual spans within the trace. To see the details of the trace, click the three-dot icon at the end of the row and select the Show Trace Details. It will bring you to the screen where you can see the trace details and the spans of the selected trace. By default, the page displays three sections. From the top of the screen, there is a Trace Details section, which tells you the trace status, number of services included, number of spans contained, trace ID, start time, and the duration. Middle of the page shows a topology view, which you can visualize the relation among the services and spans. And the lower side of the page shows the spans view, which is a bar graph showing individual spans with their durations and dependencies. In the topology view, currently operation mode is selected. So each icon represents an operation or the spans within the trace. There are two different flows in this trace. To see what they are, you can hover the mouse on the icon to see the operation name. So this is an operation that does payment verification, and here is the operation which handles the checkout. And the width of the arrow which connects the icons indicates how much time it took to connect. The wider the size, the slower the connection. So looking at the two flows in the image, you can have an idea that the checkout service took longer than the other. You can also switch the mode to show topology of the services. By moving your mouse over the arrow, it shows the connection details in a pop-up window. So this is a JDBC call which took 41 seconds to complete. Let's also look at the spans view. In this view, the spans are organized in the order they were called. It basically allows you to see the durations and dependencies of the operations that were captured within a transaction. The view has bar graphs in the format of Gantt chart, which is a method commonly used to visualize the workflow of a distributed trace. Each bar represents an operation, and the time length goes from left to right. So the longer the bar, the more time was consumed to complete the operation. The bar at the top is a root span, and child spans are nested below. From the view, you can see the trace was waiting for a SQL operation to complete, which was the bottleneck of this transaction. And to see the details of the span, you can click the bar that opens a span details view, which displays the context information of the selected span. It provides the information such as span ID, span duration, also the attributes of the span. In this example, the span is JDBC related, so you can see the related database information, including the database connection string and SQL ID, which may help you to further diagnose the database issues. You can also open thread snapshots from this page by clicking the camera icon. This view visualizes the status of the trace by the snapshots taken for each span. The snapshot contains a code stack information and is by default taken every 250 milliseconds. It is differentiated by the colors that indicate the possible reasons. So in this example, the first thread is pink, which is waiting for the network, and the second thread is purple, so it is waiting for a database. Clicking the icon opens a thread snapshot details view, which you can drill down to the method, file name, and the line number. Please note that the thread snapshot feature is disabled by default. You can enable it by updating the configuration files. Please see the APM documentation for more details. And APM is integrated with Oracle Functions. If your application uses Oracle Functions or Function as a Service in Oracle Cloud, you can enable the tracing of your function and view the spans in the Trace Explorer. In order to enable the tracing of a function, first you need to create an application, then create a function within that application. Application in this context is a logical group of functions in Oracle Cloud. In this example, that is Oaks WS Services. This is where your Oracle functions are stored. Select the Traces under the Resources to show the Traces section and ensure your Traces is enabled. When the first time the trace is enabled, you will be asked to enter the APM domain name where the spans will be sent. In this example, the configured APM domain is prod. Then go to the Functions section where you can see all your functions. In this example, the function name you want to see in the Trace Explorer is QContactBack. Ensure the tracing is enabled. By enabling the trace, your function generates a span every time the function is invoked and sends it to APM. This is done automatically and reports the response time of the function call. In addition, you can define custom spans by manually adding the code for a specific operation within the function, such as retrieving a password from a database, for example. Once the trace is enabled, you can see the spans in a Trace Explorer view. In this example, the query is extracting all the function calls invoked in the last 24 hours. Let's see the trace details of one of them. In this example, the function was called from a microservice using REST API. The blue objects refer to the function. Let's click the bar to look at the span details. Operation is function invocation. Duration is 156 milliseconds, and we can confirm that the function name is QContactBack. This is the end of the recording of Part 2, Distributed Tracing of Application Performance Monitoring Service in Oracle Cloud Infrastructure. Please find the links to other chapters of APM tutorial series from the description in this video. Thank you for watching.